Chapter 4.2, the unit circle. The unit circle is defined as a circle with a radius of 1 unit with its center at the origin of the Cartesian plane. Here's a diagram. The center of the circle is at the origin, and the circle has a radius equal to 1 unit. Label the points where the circle meets each axis. So the circle here on the positive x-axis, remember the radius is 1, then the x value would be 1 and the y value here would be 0. At the positive y-axis, again the radius is 1, this time x is 0 and y would be positive 1. At the negative x-axis, x would be negative 1 and y would be 0. And at the negative y-axis, x would be 0 and y would be negative 1. The equation of any circle is x squared plus y squared equals r squared, the radius squared. And the equation of the unit circle is x squared plus y squared equals 1. If we consider any point xy on the circumference of the unit circle, so in this picture we have a point P, xy right there, we can draw a right triangle to the x-axis and use the Pythagorean theorem to establish a relationship between x and y. This relationship holds true for any point P. So we can draw a line down to the x-axis and our radius, we create a right angle triangle where the distance from the origin to point A is the x value, and from point A up to point P is the y value. Then Pythagorean theorem, which is a squared plus b squared equals c squared, where c is the hypotenuse of the right triangle. For this triangle, we would have x squared plus y squared equals 1 squared, which equals 1. Example, write the equation of a circle with the center at the origin and a radius of 6. Start with Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse. In a circle, our hypotenuse is going to be the radius. Then we have x squared plus y squared equals 6 squared, which gives us x squared plus y squared equals 36. Example, determine the missing coordinate for all points on the unit circle, satisfying the given conditions. Draw a diagram and state which quadrants the points are in. The first one is an x value of negative 5, 8, and an unknown y value. Since we don't know what y is, y could be positive or negative. We know that this point is on the unit circle, which means the formula x squared plus y squared equals 1. Unit circle means radius equals 1. Then we can plug in our x value, negative 5 over 8 in brackets squared plus y squared equals 1. And then we can isolate the y value. So subtract negative 5 over 8 squared from both sides. We get y squared equals 1 minus bracket negative 5 over 8 close bracket squared. Let's calculate y squared. One minus bracket negative 5 divide 8 close bracket squared gives us a decimal. Math, enter, enter, gives us 39 over 64. Then we want y, not y squared, so we take the square root of both sides. But remember, when we are isolating a variable, if we square root an unknown value that's squared, we have to do plus minus, because we don't know if y started as a positive and then got squared and became a positive, or started as a negative and then when it's squared it becomes a positive. So we have to look at both cases. Then we want to simplify the radical. Becomes plus minus square root of 39 over, what's the square root of 64? 8 times 8 is 64, so over 8. And then let's double check to see if we can simplify the square root of 39. Our perfect square numbers, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared 25, 6 squared 36, and so on. We want to know if any of the numbers in that list can divide 39. The biggest number that could divide 39 to get a whole number would be half of 39. So the first number that we can even check would be 16, because everything above that is too big. So we try 16, 39 divided by 16. Do we get a whole number? No. We can try the next largest perfect square, which is 9. 39 divided by 9. Get a decimal again. And then the last option is 39 divided by 4. We get a decimal again. So that tells us that we can't simplify square root 39, which means that this would be our value for y, positive or negative, root 39 over 8. We're also supposed to draw a diagram and state which quadrants the points are in. Let's draw a Cartesian plane. Draw a unit circle. Not the best, but pretend the center of that circle is at the origin. Then if we have a negative x value, it would have to be on the left side, because that's our negative x values. So we could have 1 point in quadrant 2 and 1 in quadrant 3. Negative 5 divided by 8 is 0.6. So approximately halfway-ish for the x value, a little further than halfway to the end of the unit circle, and then go straight up from there and also straight down from there to get our 2 dots. Then we could join them to the center to create our triangles. So we'd have an x value, negative 5 over 8. And then this y value would be positive root 39 over 8. And then this y value would be the negative. And again, we're in quadrants 2 and quadrant 3. So we have 2 solutions, one in quadrant 2, one in quadrant 3. Positive root 39 over 8 for the y value, and negative root 39 over 8. Next one, we have an unknown x value and then a y value of 5 over 13. And this time it tells us that it's in quadrant 2. In quadrant 2, x is negative, so that tells us that x is negative. Start with the equation of the unit circle. X squared plus y squared equals 1. Plug in our values. X squared plus 5 over 13 in brackets squared equals 1. Subtract 5 over 13 so we can isolate the x. Then x squared equals, let's do 1 minus bracket 5 divided by 13, close bracket, squared. Math, enter, enter. We get 144 over 169. Square root both sides. We're square rooting a variable squared, so we have plus minus. And then x equals square root of 144 is 12. And square root of 169 is 13. So it'd be plus minus 13. But in this case, we are told that it's in quadrant 2. So x would be a negative, so negative 12 over 13. And we can draw a diagram. Our x value, negative 12, divide 13. We know it's in quadrant 2, but approximately where? Okay, so negative 0.9, that's pretty close to 1. So it's pretty close to the edge of the circle. So let's say about here for the x value. And then we go straight up from there to get to our y value on the circle. Then we can make our triangle. This time there's only one solution because we were told that it's in quadrant 2. So our only solution is here. Our x value is x equals negative 12 over 13. And our y value was y equals 5 over 13. Let's review the special triangles we learned in Math 20-1. The first one is the 30, 60, 90 special triangle. To create this triangle, we start with an equilateral triangle. Equilateral triangles have equal side lengths. In this case, the side length is 2, and then all equilateral triangles have angle measures 60 degrees. And this is because they all need to be equal and they all need to add to 180, and 180 divided by 3 angles gives us 60 degrees for each angle. We can draw this, so we have side lengths of 2, angle measures of 60 degrees. Then to get the 30, 60, 90 triangle, what we did was we cut this in half down the center of the triangle, which then creates 2 right triangles that are equal. So then we get this triangle down here. The bottom left angle would still be 60 degrees, it hasn't changed. The top angle was cut in half, so it's now 30 degrees. The bottom right angle is now 90 degrees. The hypotenuse is 2. It's the same as the original side length. The bottom side would be 1 because the bottom was cut in half. And then the other side we can calculate by using Pythagorean Theorem. A squared plus b squared equals c squared, where c is the hypotenuse. We have 1 squared plus b squared equals the hypotenuse is 2 squared. Then we have 1 plus b squared equals 4. Subtract 1 on both sides. We get b squared equals 3. And then we want b, not b squared, so we square root both sides, and we get b equals the square root of 3. So this side here is the square root of 3. So that is the 30, 60, 90 special triangle we learned in Math 20-1. Now we're going to adapt this triangle so that we can use it with the unit circle. We know that the unit circle has a radius of 1. When we draw a right triangle with an angle in the unit circle, the radius is the hypotenuse. So we need the hypotenuse to be 1. So we're going to divide all sides by 2. So the hypotenuse, which is the radius in the unit circle, equals 1 for the unit circle. So we divide 2 by 2, we get hypotenuse equals to 1. We take root 3 over 2 and then 1 over 2, so 1/2. Now we're going to apply this information to the unit circle, looking from this angle of 60 degrees, so our reference angle for this will be 60 degrees. The side opposite from 60 is the vertical measurement, which is the y value on the Cartesian plane, and the side adjacent to 60 degrees is the horizontal measurement, which would be the x value on the Cartesian plane. Let's draw an angle of 60 degrees and the point where it intersects the unit circle in quadrant 1. In quadrant 1, the sign for x is positive and the sign for y is positive. Then we would have x is positive 1/2 and y is root 3 over 2. Positive 1/2 is a really easy point to plot. This is 0 and the unit circle is 1, so halfway in between there would be x equals 1/2. About here, be x equals 1/2. And then from there, I can just draw a dotted line straight up to the unit circle, and then the point that lies on the unit circle when x equals 1/2 would have a y value of root 3 over 2. And I can draw my terminal arm down to my origin. And my reference angle, which is also my theta in this case, is 60 degrees. We can apply this information into all of the quadrants. Let's go with quadrant 4 next. In quadrant 4, x is a positive value and y is a negative because we're below the x-axis. X is still going to be 1/2 and y is still going to be root 3 over 2. It's just going to be negative root 3 over 2. So from my x equals 1/2 here, I can go straight down until I intersect the unit circle, and that's where my point will be. And it is x is 1/2 and y is negative root 3 over 2. Can draw our terminal arm. And our reference angle is still 60 degrees. In quadrant 2, the x values are negative and the y values are positive. They're still the same values though, because we're still talking about a reference angle of 60 degrees. So we have x is 1 over 2 and y is root 3 over 2. It's just this time we have a x value of negative 1 over 2, which is approximately there. Go straight up from that point until we intersect the unit circle, and that's where our point would lie. And it would have a value negative 1/2 positive root 3 over 2. Draw our terminal arm. Our reference angle 60 degrees. And then do the same for quadrant 4. In quadrant 4, the x value is negative and the y value is negative. Go down until we intersect our unit circle. That point would be negative 1/2 and negative root 3 over 2. We can draw our terminal arm. And our reference angle is 60 degrees. Let's look at the reference angle of 30 degrees. So our triangle has been rotated. We have 30 degrees down here, 60 degrees up here. Our hypotenuse is still 1 for the unit circle. The side across from 60 degrees is root 3 over 2, as we saw from the diagram above, and the other side is 1/2. So now we're looking from 30 degrees. The opposite side, that's vertical, would be our y value now, and then the adjacent side, that's the horizontal in the triangle, this would be the x value. So when we're looking at a reference angle of 30 degrees, our y values are going to be positive and negative 1/2, and our x values will be positive and negative root 3 over 2. Let's plot this information on the unit circle. Now I have a y value equal to 1/2, which is easier to determine the location of than root 3 over 2. So on my y-axis, I'm going to mark off 1/2. Then I just go across from that point until I meet the unit circle. My point would be here, again in quadrant 1. Our x value is positive, our y value is also positive. So we would have x is root 3 over 2, and y is 1/2. We can draw our terminal arm to the origin. And now our reference angle is 30 degrees. Then we can draw our right triangle by drawing a line straight down from that point to the x-axis. Do the same in quadrant 2. In quadrant 2, the x value is negative and the y value is positive. Going straight across from y equals 1/2 until we meet with the unit circle. X is negative root 3 over 2 here, and y is positive 1/2. Draw our terminal arm to the origin. Our reference angle is still 30 degrees, and we can draw our right triangle by going straight down to the x-axis. In quadrant 3, x is negative and y is negative. Let's plot y equals to negative 1/2. It's about here, so go straight across from there till we meet with our unit circle. That point would be negative root 3 over 2 and negative 1/2. Draw our terminal arm. Our reference angle is 30, and we can create our right triangle by going straight up to the x-axis. And then in quadrant 4, same thing, go straight across from y equals negative 1/2 till we meet up with our unit circle. In quadrant 4, we have a positive x value and a negative y value, so we get root 3 over 2 and negative 1/2. For our point, draw our terminal arm. Reference angle is 30, and we create our right triangle by going straight up to the x-axis. The second special triangle we learned in Math 20-1 is a right isosceles triangle. Isosceles triangle means that two of the sides are the same. In this right isosceles triangle, the two equal sides are 1 unit, and then the equal angles are 45 degrees. We know this because the three angles need to add to 180. It's a right triangle, so it has a 90-degree angle. Then the other two sides need to add to 90 degrees. So 90 degrees divided by two angles gives us 45 degrees. We can draw this in the diagram below. We have leg lengths of 1. Our two acute angles are 45 degrees. And we can determine the length of the hypotenuse by using Pythagorean Theorem. A squared plus b squared equals c squared. 1 squared plus 1 squared equals the hypotenuse squared. We'll just keep c. 1 squared is 1, so 1 squared plus 1 squared is 2 equals c squared. And we want c, not c squared, so we square root both sides. Then we get c equals the square root of 2, so our hypotenuse is the square root of 2. So that's the 45, 45, 90 triangle that we learned about in Math 20-1. Now we're going to modify it for use with the unit circle. We want the hypotenuse, again, to be 1. So we would need to divide all sides by square root 2. So the hypotenuse, which would be the radius in the unit circle, equals 1. So divide by root 2, then we get the hypotenuse to be 1. And then 1 over root 2 and 1 over root 2. If we rationalize the denominators, because we usually don't leave roots on the bottom of fractions, although we can in trigonometry, but if we rationalize the denominator, we can also write 1 over root 2 multiplied by root 2 on top and bottom, and we would get root 2 over root 2 times root 2 would be 2. So this 1 over root 2 or root 2 over 2. Same with this side, or root 2 over 2. Then both of our acute angles are the same. They're both 45 degrees. And our two leg lengths are the same. So it doesn't matter which angle we're looking from, we get the same result. The vertical is the y value, which would be 1 over root 2 or root 2 over 2. And the horizontal is the x value, which would also be 1 over root 2 or root 2 over 2. So the x value and the y value are the same for reference angles of 45 degrees. Let's plot this information on the unit circle just as we did for the last special triangle. In quadrant 1, x and y are both positive. 45 degrees is halfway between the two axes, so approximately here. Our angle is 45 degrees. The x value, the point where the terminal arm meets the unit circle, would be 1 over root 2 and 1 over root 2. Or we can write it as root 2 over 2, root 2 over 2. So our x and y values are the same because our angle is 45 degrees. And we can draw our triangle by taking our point down to the x-axis. And then do the same going all the way around the unit circle. In quadrant 2, the x value is negative, the y value is positive. Reference angle 45 degrees would put our terminal arm halfway between the two axes, approximately there. Our reference angle is 45. Then the point would be negative 1 over root 2 and positive 1 over root 2, or negative root 2 over 2 and positive root 2 over 2. We can draw a triangle by joining our point to the x-axis. And in quadrant 3, x and y are both negative. Reference angle of 45 degrees would be halfway between the x and y axes, approximately here. Then the point where the terminal arm meets the unit circle would be negative 1 over root 2 and then negative 1 over root 2 for the y value as well. Or we can write it as negative root 2 over 2 and negative root 2 over 2. And we can draw our right triangle by joining the point to the x-axis. Our reference angle is 45 degrees. And then lastly, in quadrant 4, the x value is positive and the y value is negative. A reference angle of 45 puts our terminal arm halfway between the two axes, approximately here. Our reference angle is 45. The point where the terminal arm meets the unit circle would be positive 1 over root 2 and negative 1 over root 2, or positive root 2 over 2 and negative root 2 over 2. Now we need to put all the information together on a single diagram. So you have a worksheet, should say 4.1 worksheet, have a big picture of the unit circle. You do not get any information about the unit circle for the diploma. So you need to know the information and be able to fill out all this information about the unit circle, determine the reference angles, determine the points where the terminal arm of each reference angle meets the unit circle. So you want to look for patterns. We're going to look at quadrant 1, and then you should be able to apply the information to all the other quadrants. So starting with a reference angle of 0, which is when our point is on the positive x-axis, the coordinate point would be x is positive 1 and y is 0. The next one, our smallest special angle that we talked about, was 30 degrees. So to this point is 30 degrees. And what is that in radians? We can convert it. 30 degrees times pi over 180 degrees would equal 30 degrees times pi over 180 degrees. We can divide out 30, so we get pi over 180 divided by 30 is 6. So our radians is pi over 6. The next smallest special angle we talked about was 45 degrees. So our terminal arm goes to this point. And then this angle is 45 degrees. And let's convert that. 45 degrees times pi over 180 degrees, which gives us 45 degrees times pi over 180 degrees. Divide top and bottom by 45. We get pi over 45 times 2 is 90, so 45 times 4 is 180, so pi over 4. So the radian measure for 45 degrees is pi over 4. And then we can do the next dot here, which would be our reference angle of 60 degrees that we talked about. Convert that. 60 degrees times pi over 180 degrees equals 60 degrees times pi over 180 degrees. Can divide both by 60. We get pi over 180 divided by 60 is 3. So pi over 3 is the radian measure for an angle that is 60 degrees. And then if we look at 90 degrees, that would give us this point up here, which on the unit circle, the radius is 1, so our y value would be 1, and our x value would be 0. And then what we need to do is be able to determine the x and y values for these points here. There are special angles from our special triangles. So if we can draw our special triangles, then we can figure this information out. Our first special triangle started as an equilateral triangle. with side lengths 2, angles of 60. We divided it down the middle. Then we got a right triangle from that. Bottom left angle still 60. Top angle got divided by 2, so now it's 30. And then we have our right angle. Hypotenuse is 2. Bottom side is 1. And then we calculated the other side to be root 3 using Pythagorean Theorem. But then for the unit circle, we need the hypotenuse to be 1. So we divide by 2, divide by 2, divide by 2. Then our hypotenuse is 1, and our other sides are root 3 over 2 and 1 over 2. When our reference angle is 60 degrees, and I look at the side opposite of 60 degrees, that's my vertical, which is my y value, and my bottom side is my horizontal, which is my x value. So for the point where the terminal arm for the angle 60 degrees meets the unit circle, our coordinate point would be positive 1/2 and positive root 3 over 2. Then we can rotate this triangle so that the 30 degrees is in the bottom left. Bottom left angle is now the 30 degrees. Top angle is 60. Our right angle is in the bottom right still. Our hypotenuse is 1. The side opposite from 30 is 1 over 2. And the side adjacent to 30 is root 3 over 2. The side opposite is the vertical, so that would be the y value now. And the side adjacent is horizontal to 30 degrees, so that would be the x value. So for a reference angle of 30 degrees, the terminal arm meets the unit circle at the point x is root 3 over 2 and y is 1/2. And then we have the reference angle of 45 degrees. We can draw the 45, 45, 90 special triangle. It's an isosceles triangle, so these two sides are equal and these two angles are equal. We have a right angle. Our two sides start as 1, which made our hypotenuse square root 2. Our angles are 45. But then for the unit circle, we need our hypotenuse to be 1. So we divide everything by root 2. So then we have the x value and the y value for reference angles of 45 degrees are 1 over square root 2. Or if we write this with a rationalized denominator, then it would be root 2 over 2. Any quadrant that you move to, if your reference angle is one of these values, 30, 45, or 60, the x and y value will be the same as they are here. The only difference will be the sign is changing. So then we have the cast rule from Math 20-1, which talked about the sign of the trig functions, sine, cos, and tan in each of the quadrants. In quadrant 1, all trig functions are positive. In quadrant 2, sine is positive. In quadrant 3, tan is positive. And in quadrant 4, cos is positive. So it's called the cast rule because if you start in quadrant 4, then it's C-A-S-T, cast. And then in terms of the x and y values in each quadrant, in quadrant 1, we have positive x, positive y. In quadrant 2, x is negative, y is positive. In quadrant 3, they're both negative, so negative x, negative y. And in quadrant 4, we have positive x, negative y. Now let's put this into practice. If P theta is the point at which the terminal arm of angle theta in standard position intersects the unit circle, determine the exact coordinates of each of the following. So P is a point, an xy value. We want to determine what P is. So P of pi over 2. Pi over 2 is a quarter of the way around the unit circle, so that's 90 degrees. We can add that to our picture here. All the way to our positive y-axis is 90 degrees, which is pi over 2 radians. And when we have an angle of pi over 2, the point where the terminal arm intersects the unit circle is at x equals to 0 and y equals to 1. Let's draw a little diagram. P of pi over 2 would be right there. P of 2 pi over 3. When you're working with angle measures in radian, my best suggestion is to simplify the fraction first, so fully reduce it. Then if you still have a denominator, your denominator will either be 3, 6, 4, or 2, and then you can look at quadrant 1 of the unit circle and your reference angle will be the same. So if your denominator of your reduced radian measurement is a 6, then it's going to have the reference angle pi over 6, and our point will be root 3 over 2 and 1 over 2. And then the signs for those x and y values will change depending on which quadrant you're in. If your denominator is 4, then you're using the reference angle pi over 4. So you get this point, root 2 over 2, for both x and y, and again, your signs will depend on which quadrant you're in. If you have a denominator of 3, you're using pi over 3 as your reference angle, and your point is 1/2 for the x value and root 3 over 2 for the y value, and then the sign depends on the quadrant you're in. And if you end up with a 2 as your denominator, then you're either going to be at the positive y-axis or at the negative y-axis. So your x value will be 0 and your y value will either be positive 1 or negative 1. And then if you end up without a denominator, you're either at the positive x-axis, so you have 0 or 2 pi or 4 pi, or you're at the negative x-axis, which would be 1 pi or 3 pi or 5 pi, etc. So your x value would be either positive 1 or negative 1, depending which axis you're on, and your y value would be 0. So P of 2 pi over 3, can we reduce the fraction 2 pi over 3? No, we can't. So that means that pi over 3 is our reference angle. And then we have to decide which quadrant 2 pi over 3 is in. To do that, we should know some basics. We know that this starts as 0, and then when we get all the way around, it goes back to 2 pi. The positive y-axis is pi over 2. The negative x-axis is pi. And then the negative y-axis would be 3 pi over 2. So 2 pi over 3 is bigger than pi over 2, because 3 over 2 is bigger than 1/2. But it's smaller than pi, because that would be 1 whole pi, whereas we have 2/3 of a pi. So it's got to be in this quadrant, and our reference angle is pi over 3. Then our angle is 2 pi over 3. 2 pi over 3 plus pi over 3 gives us 3 pi over 3, which is pi. So we know we did that correctly. Then the point that would intersect with the unit circle, so we have a reference angle of pi over 3 in quadrant 2, which means x is negative and y is positive. Then our point is reference angle of pi over 3, this one 1/2 and root 3/2. In this case it's negative 1/2 and positive root 3/2. So my suggestion would be every day before you start your practice questions, before you start your trig lesson, before you write your quiz, before you write your unit test, whatever you're doing, the first thing that I would recommend you do is drawing your special triangles and determining the x and y values for each of the special angles, and then drawing quadrant 1 of the unit circle and putting all of that information on there, including the angle measure in degrees and also in radians. Then you can reference this diagram after you've created it to use to answer questions such as the ones we're answering now. Next one, p at negative pi over 6. Can we reduce negative pi over 6? No, we can't reduce that at all. So this tells us that theta r is pi over 6. Then we have to determine which quadrant this is going to be in. Negative angles, you go clockwise. So pi over 6 going clockwise, a reference angle of pi over 6, and negative pi over 6 would just be down below the positive x-axis. Draw our unit circle. Our reference angle theta r is pi over 6, and our angle theta is negative pi over 6. So we're in quadrant 4 with a reference angle pi over 6 in quadrant 4, and in quadrant 4 we have a positive x value and a negative y value. Go back up to our picture of quadrant 1 of the unit circle and look for pi over 6, which is this angle here. And our x value is root 3/2, our y value is 1/2. In this case, we're doing positive x, so root 3/2, and then negative y, so negative 1/2. Next one, p at negative 17/4. Start with, can I reduce this fraction at all? No, can't reduce that. There's nothing that divides 17 and also divides 4. So then our reference angle would be theta r equals pi over 4. We have a negative direction, so we know that it's going to go clockwise. So it's gonna go this way. It's bigger than 2 pi, because 2 pi would be 8 pi over 4. So it's gonna go around 1 full time for sure, that's 8 pi over 4. And then if we did another 8 pi over 4, that would be 16 pi over 4. So it goes around 2 full times. And then we just need to go 1 more pi over 4, and that would be negative 17 pi over 4. So we're going 1 more pi over 4, which brings us to halfway between these two axes in quadrant 4. Our reference angle, theta r, is pi over 4. Our angle is negative 17 pi over 4. We're in quadrant 4, so we have a reference angle pi over 4 in quadrant 4, which means x is positive and y is negative. Reference angle of pi over 4, it's really easy. That's where they're both the same. They're both root 2/2 or 1/√2. The point on the unit circle at negative 17 pi over 4 is positive root 2/2, negative root 2/2. State two different possible measures for the rotation angle theta such that p of theta equals negative 1 over 2 and negative root 3 over 2. Write a general statement for all such angles. X is negative and y is negative. In which quadrant are they both negative? That's in quadrant 3. So our point is in quadrant 3. I can draw a diagram. We have an angle in quadrant 3. Doesn't really matter where I draw it, just draw an angle in quadrant 3. And our point is on the unit circle at the end of that terminal arm. We want two different measures for the rotation angle. So we could have the angle going the positive direction, that could be our theta 1. We could also measure from going the negative direction as our theta 2, and then our reference angle is here, theta r. So we need to figure out the reference angle for this point. We know that it's not going to be 45 degrees or pi over 4 because that point we have the same x and y value, root 2 over 2 or 1 over root 2. So it's not that. So it's got to be our other special triangle. So we could start by drawing our 30, 60, 90 special triangle. I'm going to put it at the top here. So we start with an equilateral triangle, has side lengths 2, angle measure 60. We cut it in half down the center. Then we get a right triangle that has angle measure 60, 90, and 30 at the top. We still have 2 for the hypotenuse. We have 1 for the bottom because it was cut in 2, and then we get square root 3 for this side. Then we need to modify for the unit circle, make the hypotenuse 1, so we divide all the sides by 2. So we end up with our angles 30, 60, 90. Our hypotenuse is now 1. Our right side is root 3 over 2, and our bottom is 1/2. So if we're looking from 60, that would give us a y value of root 3 over 2 and an x value of 1/2. Is that what we have in our point here? Yes. X is 1/2 and y is 3 over 2. So 60 is our reference angle. Therefore, 60 degrees, or what is 60 degrees in radians? It's pi over 3 is our reference angle. Okay, so we know the points in quadrant 3, and we know that theta r is 60 degrees or pi over 3. Let's calculate theta 1 and theta 2 then. So theta 1, going the positive direction, we would have 180 degrees, which would cover quadrants 1 and 2, plus theta r, our reference angle, so 180 degrees plus 60 degrees in this case, which gives us 240 degrees. And then theta 2, if you're going the negative direction, you can start by taking the positive value for that angle, so 240 degrees, and then subtracting the total distance to go around the circle, so 360 degrees, and that leaves us with negative 120 degrees. Or we can write this in radians. Theta 1 equals quadrants 1 and 2, so when we get to the negative x-axis, that's pi, a measure of pi radians, plus our theta r, reference angle, which is pi plus pi over 3. Pi would be 3 pi over 3 plus 1 pi over 3 would give us 4 pi over 3. And then for theta 2, Same thing, start with the positive measure of the angle, 4 pi over 3, and then subtract the measure going all the way around, which is 2 pi. 2 pi is equivalent to 6 pi over 3, so 4 pi over 3 minus 6 pi over 3, which gives us negative 2 pi over 3. So those are our two different measures for our angles in degrees and then in radians. Next, we want to write a general statement for all angles in this position, because there's an infinite number since we can go around and around and around in both the positive and the negative direction. First, for degrees, we would have theta equals the principal angle, which is 240 degrees. And then we would have plus 360 degrees times n, where n is an element of the integers. The difference between this one and the general statement we wrote in 4.1 is that in 4.1 we were talking about the general statement for angles that were coterminal only. Writing the general statement for coterminal angles, if you calculate the general statement, it won't include the angle you started with. However, writing the general statement for all such angles is different than coterminal. This means if I plug in an n value here, that's an integer, so positive whole number, negative whole number, or 0, then I will get all angles that have a terminal arm in this location, including 240. Because if I plug in 0, which is an integer, then this is 0, so I have 240 plus 0, which is 240. If I plug in negative 1 here, then it's going to start at 240 and go backwards a full rotation, which would get us to negative 120. Okay, so that's why in this case we have n is an element of the integers instead of n is an element of the natural numbers, which only includes the counting numbers, 1, 2, 3, 4, etc. And also why we just have a plus, we don't actually have to write a minus here, because since it's integers, putting a negative number in for n is like subtracting. So we just have to write the angle, the principal angle, plus 360n, comma, n is an element of the integers. Or if we write it in radians, then theta equals 4 pi over 3 plus 2 pi is a full rotation, so 2 pi n, where n is an element of the integers. Those are our two general statements that represent any angle that has a terminal arm in the same location as our angle, which is here. The points A, 0, 1, and B, negative 1 over root 2, 1 over root 2 lie on the circumference of the unit circle. Determine the arc length AB. Since x and y are the same, 1 over root 2, 1 over root 2, those come from our special triangle where the reference angle is 45 degrees. So this point tells us that theta r is pi over 4, or 45 degrees. It also tells us the quadrant because the x value is negative and the y value is positive. So it's in quadrant 2 because negative and positive. Let's draw a diagram. We have a reference angle of 45 degrees or pi over 4 in quadrant 2. Draw our unit circle. This point is negative 1 over root 2 and positive 1 over root 2. And then it also gives us the point A, which is 1, 0. So x equals 1, y equals 0 would be here. We want to know the arc length between the 2 points. So that is the measure of how long this portion of the unit circle is. Remember, arc length formula is theta equals A over R. So we need to know theta in radians. Has to be in radians to use the arc length formula. And we need to know the radius. It's on the unit circle, so the radius is 1. We need to know theta then to calculate A. So theta would be here. We need to figure out what that is in radians, remember. So theta would equal, quadrants 1 and 2 together would be pi. Subtract theta r, which is pi over 4. Pi would be 4 pi over 4. Subtract pi over 4 gives us 3 pi over 4. Then we can use the arc length formula. Theta equals A over R. Theta in this case is 3 pi over 4. A is what we're calculating, R is 1. We can cross multiply and divide. 3 pi times 1 divided by 4 gives us A equals 3 pi over 4. And we can calculate that because usually a length we want as a decimal answer. 3 pi divided by 4, we get 2.3561. Or if we round to the 10th, A equals 2.4 units. The length of the arc on the unit circle that starts at A equals root 3 over 2, 1/2, and ends at point B after 3/4 positive rotation. Find the coordinates for B and the arc length. Since we want arc length, we are going to have to use radians. And it tells us it's on the unit circle, so we know that R equals 1. I can start a diagram. If the point A is at root 3 over 2 and 1/2, they're both positive, so it's in quadrant 1, and Y is 1/2. So if I go straight across from 1/2, because I know if I go to the edge of the circle on any axis, then that's 1 unit. So I go to Y 1/2, put a dot across from there, join my origin to that dot, and there is point A. I need to know the angle for point A. I know that it's going to be my 30, 60, 90 special triangle because I have root 3 over 2 and 1/2. So I can draw my 30, 60, 90 special triangle. Another way you can think about it, let's just draw quadrant 1 of the unit circle. We have 3 special angles. The first one is when y equals to 1/2. So if I go straight across from y equals to 1/2 and put a dot, that's my first one. It's my smallest angle. Then I have one where the x and y value are the same, which gets me right in the middle of the 2 axes. So let's say about here. And that's my reference angle, 45 degrees. So root 2 over 2, root 2 over 2. And then I have my third one, which is then when the x and y values switch from the first one. So now my x value is 1/2. So let's say about here. Go straight up from x equals 1/2 and then join your origin to that point. So then we have the smallest one the medium one, which is a reference angle of 45 degrees or pi over 4, and then the largest one, which is 60 degrees or pi over 3, and the smallest one is 30 degrees or pi over 6. Now, the points for 30 degrees and 60 degrees are just switched. The x and y values, we still have the same two fractions. They're just switched. So in this one, which value was 1/2? The y value was 1/2 for the lowest one. So 1/2, which means the other one has to be root 3 over 2. And then in the bigger one, the theta equals to 60 degrees or pi over 3, we have an x value of 1/2 and a y value of root 3 over 2. So that's another way to think about it, looking at which of our values is 1/2 for the 30 and 60 special angles, and then would that be the lower angle? So if y is 1/2, that would be the lower angle. If x is 1/2, that would be the higher angle. So from this information in our question that we're currently doing, this tells us that our reference angle theta r equals 30 degrees or pi over 6 radians. Okay, so now we have that. We know that the reference angle for point A is pi over 6, or the angle for point A is pi over 6. So theta A is pi over 6. Then we need to figure out where this other point is. It's 3/4 of a rotation away from A. 3/4 of a rotation. What is 3/4 of a rotation in radians? We can take 2 pi of full rotation and multiply it by 3/4. Then we get 6 pi over 4, which reduces to 3 pi over 2. Then to get theta b, we start at theta a, pi over 6, and we add 3/4 of a rotation, which is our 3 pi over 2. I need to make a common denominator, so I could multiply this fraction by 3 on top and bottom to get pi over 6 plus 9 pi over 6, which gives us 10 pi over 6, which reduces to 5 pi over 3. Then, since the reduced fraction has a denominator of 3, this tells us that theta r, the reference angle for point B, is pi over 3. And what quadrant is 5 pi over 3 in? If we start at the positive x, that's 0. This is pi, which we can write as 3 pi over 3. And then when we get back to the 0, it becomes 2 pi, which we can write as 6 pi over 3. So 5 pi over 3 is 1 pi over 3 less than 6 pi over 3. So it'd have to be in quadrant 4 down here. And what are the x and y values for that point? Well, if we go to this diagram again, for pi over 3 is bigger than pi over 6, right? So pi over 6 is our small angle. Then we have pi over 4 is the middle one, and then pi over 6 is the bigger one. And for pi over 6, we have an x value that's 1/2 and a y value that's root 3 over 2. We're in quadrant 4, so x is positive, y is negative, so negative root 3 over 2. We can draw that on our other diagram. This is point B. And then we want to know the arc length between A and B after a positive rotation. So positive rotation, we are going this direction to get from A to B, and we're trying to determine the arc length. So first of all, we need to figure out the angle between them. So theta. What is theta? The angle between A and B. We know that theta A is pi over 6, and then the reference angle for B is pi over 3. We're doing the arc length now. Start with 2 pi and subtract pi over 6 and subtract pi over 3. We can write 2 pi as 12 pi over 6 minus pi over 6, and then we can write minus pi over 3 as 2 pi over 6. Then we subtract 12 minus 1 minus another 2. 12 minus 3 would be 9 pi over 6, which reduces to 3 pi over 2. And then we can use our arc length calculation. Theta equals A over R. In this case, theta is 3 pi over 2. We don't know A, and R is 1. Cross multiply and divide. We get A equals 3 pi over 2. Or we can calculate it. Three pi divide 2 gives us 4.71. So rounded to the 10th, I'll do 4.7 units. And the question also asked for the coordinates for point B. B is 1/2 and negative root 3 over 2. So you can see from these questions, you really have to know the unit circle. You really need to know how to get each of the angles, where they are in quadrant 1, what the x and y values are, and then be able to use reference angles and signs of x and y to determine values in each of the quadrants. That brings us to the end of Lesson 4, Chapter 2.